Hello, my students. This last video will instruct upon electrolysis. Remember, we first started the chapter by saying electrochemistry is all about getting electrical work out of a chemical reaction, or using electricity to make a non-spontaneous process spontaneous. Well, that is what we do with electrolysis. We talked about, for electrons to flow, there needs to be a cell potential, a natural pull or push for electrons, a natural downhill for electrons to flow. Well, the reason why a non-spontaneous process is non-spontaneous in the terms of electrochemistry is it's an uphill, and electrons won't naturally flow and put in the work to move up the hill. But if we ourselves insert a voltage, we can turn an uphill into a downhill, and then electrons will flow. So the voltage being inserted actually reverses the hill, if you will, making it a downward slope, and electrons will flow. So that is the goal of electrolysis. To minimize and to put ourselves at ease, all that we'll need to be able to master with electrolysis is the dimensional analysis. So the math analysis that you would be asked to do to accomplish something like plating copper on a penny, or the production of aluminum, and so on. So it's really just being able to understand the dimensional analysis involved with electrolysis. So let's get some terms. In electrolysis, you use an electrolytic cell instead of a galvanic or a voltaic cell. An electrolytic cell uses electrical energy to produce the chemical change. Because electrolysis requires forcing a current through the cell, which will produce a chemical change for which the cell potential is negative, which means it's non-spontaneous. Or we can simply say electrolysis is causing a non-spontaneous chemical reaction to occur. There's so many examples of electrolysis in our daily lives. For example, when you plug in your cell phone to recharge, you are using an electric current to reverse a non-spontaneous reaction. The spontaneous reaction produces the electrons that then power your cell phone or your MP3 player, etc. Remember that a galvanic or voltaic cell, and this is an example of it, is spontaneous, because we are allowing whatever wants to be the reduction and whatever wants to be the oxidation to occur. There is a natural pull and push which produces a positive EMF value for the cell, 1.1 volts in this circumstance. So as we see here, the zinc is being oxidized and the copper is being reduced. That's the natural flow that will create a spontaneous reaction. Well, what if we wanted the reverse? Well, that is where the electrolytic cell comes in. What if we wanted the copper to be the oxidation and the zinc to be the reduction? We'd have to apply a voltage greater than the 1.10 volt. We'd have to attach a battery or some kind of power supply. As soon as we exceed the minimum voltage for the spontaneous reaction, then this reaction will occur, and we will undo the reaction that happened that was spontaneous. So this is a great example of how a battery would be recharged. So in this voltaic cell, if you can imagine what we would visualize, the zinc electrode would be creating zinc ion. So we'd get less and less and less of this solid present, and the copper solid would be collecting on the copper electrode, and this would become less and less and less blue in color. However, whenever we reverse the process, we would get zinc ion to deposit a zinc solid, so we would recreate this electrode, and we would pull, if you will, solid copper back into solution as copper ion, again reversing the process. Before we continue onward, we need to get some terms. We've been working with voltages. Well, now we're going to get an electrochem term, an amp. A volt measures the potential difference. An amp measures the flow of the current. I found a great, better explanation of the difference between voltage and amps. If we think of water and think of the pressure of the water versus the flow of the water, the pressure of the water versus the flow. The flow of the water is due to the volume of water that's there. That's what amps are conveying. With the pressure of the water, that's what really reveals the push behind it. So volts are what push the electrons through the wire. If we didn't have a cell potential, the electrons would just be in their sea of electrons. It would just be meandering through the wire. Amps is the flow, but without voltage, there would be no reason for the water to flow or the electrons to flow. Voltage, remember, is energy per coulomb, and amp is coulomb per second. Again, a volt is a joule per coulomb, and amp is a coulomb per second. So it's the rate, if you will, the flow. On the second page, I just like what Wikipedia gave to compare an electrolytic versus a galvanic cell. And I just starred this certain sentence. Electrolytic cells undo the effect of spontaneous chemical reactions, and thus energy must be provided in the form of electrical energy that puts the electrolyzed chemicals in a higher energy state than in the normal inert form. So again, we are reversing the uphill hill to make it a downward flow for our electrons. So let us tackle our first example. All right. So if we're looking at the stoichiometry of the electrolytic process, we're usually analyzing and trying to figure out how much chemical change can happen once we apply a certain voltage over a certain amount of time. So let's just explain this as we walk through this example. Now this first example, I will break it down into individual steps, but eventually we can solve it as one-dimensional analysis problem. All right, so we're asked to determine the mass of copper. So that is our end goal, the mass of copper that can be plated, for example, laid on a zinc template, like in the like what we know makes up a penny. Determine the mass of copper that is plated out when a current of 10 amps is passed for 30 minutes through a solution of copper +2. Can we visualize what's going to happen here? We're applying a voltage, so copper +2 will plate as copper solid. To do this, each copper +2 ion needs to take on or be reduced by 2 electrons. So we know from this there are 2 moles of electrons for every 1 mole of copper +2 ion. Well, first, let's try to interpret the currents. All right, now, we're given that it's 10 amps, which means there's 10 coulombs for every 1 second. Well, we're told that we're using a time of 30 minutes. So we know that there are 60 seconds per minute, and we are putting it through a total of 30 minutes. So what we've done here is just gotten the total amount of charge that is available, or that we're putting into our solution, which was sig figs, 1.80 times 10 to the 4th coulomb. All right. We know that we're applying electrons, and through the Faraday constant, 1 mole of electrons is 96,485 coulombs. Okay. Well, we're putting in 1.80 times 10 to the 4th coulombs, and Faraday's constant, 96,485 coulombs in every 1 mole of electrons. so what we are actually inputting is 1.87 times 10 to the minus 1 mole of electrons into our solution. So if it's 1.87 times 10 to the negative 1 mole of electron, well, we know that for our reaction to take place, we need 2 moles of electrons for every 1 mole of copper plus 2 ion. And, for every 1 mole of copper plus 2 ion, it's going to provide us 1 mole of solid copper. I'm going to continue to get the mass of my copper. We know that 1 mole of copper is 63.55 grams per mole. And so, doing this math, that will plate for us 5.94 grams of copper. So what we did, we started with the amperage, incorporated the element of time, used our knowledge of what must have happened to be able to plate out solid copper from the copper ion solution, Faraday's constant, to eventually get us to the mass of the copper that must have come out of solution. I'd like to create a part 2 video that will lead us through the rest of the problems within this packet.